Hi, everybody. It's Professor Mitchell, and we're continuing with Chapter 8. Today, we're looking at Section 8.3 on trigonometric integrals. In this section, we're going to look at some tricks on how to integrate certain combinations of trig functions. So let's start with this example. The way that I like to present this is to take an example, kind of walk you through it, and then after that, talk about how it works in general. So we're starting with powers of sine and cosine. This section is divided into really two major parts with a couple of other miscellaneous things thrown in. So let me switch over to the tablet where we will talk through this example. All right, so notice that this integral involves an odd power of cosine. So what I'm going to do with that is I'm going to break it into cosine squared, 4x times the cosine of 4x. Now remember, you have these this Pythagorean identity that relates sine squared and cosine squared. So what I'm going to do now is use that to rewrite this cosine squared 4x. I'm going to write it as 1 minus sine squared 4x. All right, and now we can do this as a substitution. If we let u equal sine 4x, that's going to make du cosine 4x times 4, right? Because of the chain rule. All right, so then, shoot, I wish I had done one other thing first. Oh, let's see, what would be the, okay, let's do this. I should have done one other thing. I'm still going to use this substitution, but before I do, I want to break this into two separate integrals. So if we distribute cosine 4x dx, we're going to get the integral cosine 4x dx minus integral sine squared 4x cosine 4x dx. All right, at first I thought I could use my substitution on the whole thing, but that one mixed in there would have created some minor problems. So I am going to use this substitution on the second integral. The first integral is just what I call a baby u substitution. So this will evaluate to just 1/4 sine 4x. We will need a plus c here somewhere, but I can just put that at the end. And then, let's see, I'm going to be replacing cosine 4x dx with 1/4 du. I'm going to be careful about that. All right, so this second integral is going to turn into 1/4 integral u squared du. Let's see, can I squeeze this in here? So we're going to have 1/4 sine 4x. And of course, the integral u squared is u cubed over 3. So that's going to be u cubed over 12 plus c. But it's not about u, so I will write this final answer as 1/4 sine 4x minus 1/12 sine cubed 4x. plus c. All right, and that's the idea with what you do when you have an odd power of cosine. You do something very similar when you have an odd power of sine. So let's talk about that. Going back to the presentation now, when I was reviewing my PowerPoint here, I noticed that I only had what you see here on the left side. The last time I taught this class, it was face-to-face. So I would have told the class this part. And of course, I would have told you the same thing, but I thought it might be a good idea to also type it out on here. So if you want, don't pay too much attention to what's on the left side. You know, they have a knack for making everything sound complicated. I like to make it sound very logical, and this is very logical. So there are three cases or three situations that can happen when you have powers of sines and cosines. And let's start with the second one because we just looked at that. If the cosine power is odd, you're going to break off one cosine factor and convert the other cosines to sines, and then use substitution. And that's what this says here under case 2. Wait a minute. Yeah, case 2. All right, and you do the same thing if the sine power is odd, the same type of thing. If the sine power is odd, you're going to break off one sine factor and convert the other sines to cosines. And then your substitution will be u equals cosine x, or whatever letter you want to use. It doesn't have to be u. All right, now there is one annoying miscellaneous case. What if your sine power is not odd and your cosine power is not odd? In other words, all of the powers are even. Well, then you do something completely different because none of this is going to work. You have to use what I call the power reducing formulas. I think some instructors call these the half angle formulas to reduce the integrand to lower powers of cosine 2x. And we will look at an example of that. All right, so here are the examples I have, just 2 of them for powers of sine and cosine. So let's switch over back to the tablet. All right, and here's our first example. So again, it is an odd power of cosine. So what I am going to do is break that odd power of cosine into cosine squared and cosine. Okay, so when you eventually get to the point of doing your substitution, this is going to take up most of your du, all right? Which means that u needs to be some kind of sine. And that means we need to take this cosine squared and rewrite it using the Pythagorean identity. So leave this sine squared alone and rewrite this cosine squared as 1 minus sine squared. All right, now okay. After what happened in the last example, I think in this example I can actually do my substitution now. I don't think I have to break this into 2 separate integrals, but we'll see. All right. So u is going to be sine 2 theta du then will be cosine 2 theta times 2. All right, which means cosine 2 theta is going to get replaced with 1/2 du. All right. Yeah, I think this will work. So what we have then is the integral u squared times 1 minus u squared. And then cosine 2 theta d theta gets replaced with 1/2 du. Okay, now this is a definite integral. And you know that I like to change the limits of integration on those. And I just noticed that something kind of fun is going to happen with this one. Theta goes from 0 to pi over 2. U is sine 2 theta, which means that u is going to go from sine 0, which is 0, to sine pi, which is also 0. This is one reason I like to change my limits of integration when I do substitution, because this happens about one time out of every, I don't know, maybe 20, right? It ends up that your limits of integration are the same. And I believe a couple sections ago in that first section of chapter 8, they talked about this a little bit, that when you have an integral where the limits of integration are the same, you don't have to do anything else. That integral is going to evaluate to 0. All right, isn't that nice? So now let's look at the next example. Okay, so this is what they call case 3, where there are no odd powers. It's just cosine to the 4th of something. So this is where we have to use the power reducing formula. Before I use the power reducing formula, I am going to rewrite that cosine to the 4th as cosine squared and then squared. Okay. All right, so let's review that identity, because sometimes people get confused, well, with this identity, all right, with making certain types of substitutions. So the identity is cosine squared, and let's just say blank, is equal to 1 plus the cosine of 2 blank over 2. So what goes in the blank in this case is a 2 pi x, which means that's what I have to put in the blank over here. All right, so my cosine squared 2 pi x is going to get replaced with 1 plus cosine 4 pi x over 2. And that whole thing gets squared. Okay. All right, so now what I have to do is multiply this out. First, let me point out that when I square this fraction, the denominator is going to be a 4. Let's take that 4 and divide it into the 8, and that'll just make this a 2. Okay. So no more fraction in the integrand. We're going to square 1 plus the cosine of 4 pi x, and that's going to give me 1 times 1 is 1. 1 times cosine 4 pi x plus another 1 plus 1 times cosine 4 pi x is 2 cosine 4 pi x plus cosine squared 4 pi x. All right. So this is no problem. This is no problem. That's going to be a baby u substitution. This right here is an even power of cosine. So we have to use that power reducing formula again. Okay. All right, so let's leave everything the same, except, okay, now just imagine that in the box here, oh, well, we don't have to imagine, do we? I could just write it over top. So now this is a 4 pi x. This is a 4 pi x. So now what I'm going to put here is 1 plus cosine 8 pi x over 2. All right. And this is going to be a little messy. And I think rather than flip over to the next page, let me just erase what's up here. Okay, maybe do some cleanup with this integral before we start actually integrating. Okay, so we have 2 times the integral. So now imagine breaking this into 2 fractions. You would have a 1/2 plus another term. What I want to do with that 1/2 is combine it with this 1. So that's going to give me 3/2. This is fine just the way it is, 2 cosine 4 pi x. And now over here, we're going to have a 1/2 cosine 8 pi x. All right, so now I think I'm ready to start integrating. The integral of 3/2 with respect to x is 3/2 x. Okay. So now let's talk about the integral of 2 cosine 4 pi x. That's going to be 2 times, by baby u substitution, it's going to be sine 4 pi x times 1 over 4 pi. Okay. And then the same type of thing over here. It's going to be 1/2 sine 8 pi x times 1 over 8 pi. Okay. So now let's just pretty this up a little bit. It's not going to get a whole lot prettier. When you distribute that 2, that's going to get rid of this 2. That's going to put a 2 there, and then this 2 is going to kill off this 2. And then we can forget about this 1/2. All right, so we're going to end up with 3/2. I don't need the parentheses, do I? Oh, I didn't, oh yes, I did, because I had the 2 outside. All right, but I don't need them anymore. 3x plus 1 over pi sine 4 pi x plus 1 over 8 pi sine 8 pi x plus c. Isn't that fun? I will admit that this is my least favorite type of integral involving sines and cosines, because it does end up being quite a bit more work than the ones that have odd powers. All right, so while we're on the topic of sines and cosines, you can use that power reducing formula in a problem like this. So they want us to evaluate the integral from 0 to pi of the square root of 1 minus cosine 2x. So again, use the power reducing formula. I will show you how that works. All right, so remember the power reducing formula that has the minus in it, this minus right here, is the one for sine squared x. So that formula says sine squared x equals 1 minus cosine 2x over 2, which means that we can replace that 1 minus cosine 2x with 2 sine squared x. Notice that 2 will be under the square root, so we have the square root of 2 sine squared x dx. All right, now I want to be super careful here. The square root of 2 sine squared x would be the square root of 2, which I will put out here, times the square root of sine squared x. In general, remember that the square root of u squared, I think we talked about this once, is the absolute value of u, all right? So until I see what's going on with my limits of integration, I'm going to write that as absolute value sine x. All right, now sine x, is it positive or negative between 0 and pi? Well, fortunately, that is the top half of the unit circle. Sine x is the y coordinate on that unit circle, which means throughout the interval 0 to pi, sine x is non-negative, which means it turns out in this case that we don't need the absolute value. If it had been a cosine x, it would have been a different story. All right, so this turns out to be pretty easy once you get it down to that point. The integral of sine x is negative cosine x. So we have negative root 2 cosine x. Plug in pi, plug in 0. And that's going to give us the cosine of pi, which is negative 1, minus the cosine of 0, which is 1. And the value of this definite integral is negative root 2 times negative 2, which is 2 root 2. Okay, so now we come to the next major topic in this section, which is powers of tangent and secant. These are, well, they take a little more thought maybe than the powers of sine and cosine, and I think that's because the derivatives of secant and tangent are maybe just a little harder to remember. Remember that the derivative of secant is secant times tangent, and the derivative of tangent is secant squared. So, but the sort of general strategy is the same. We're looking to set up a substitution. All right, so we'll do this as our first example. I'll kind of talk you through it, and then I'll tell you what the sort of general rule is. So switching over to the tablet. All right, so in this example, we have an even power of secant. And whenever you have an even power of secant, what you want to do is break off a secant squared factor, which is going to leave me a secant squared factor. I'm going to put the other secant squared factor at the end, because that's going to make up the du in my substitution. All right, and then I'll keep this tangent squared x. All right, so the not ultimate goal, but how we're going to get there is we're going to let u equal tangent x, which is going to make du secant squared x dx. So we need to write all the rest of the parts of this integral using tangent. And I've said this to you several times before. Literally every time I need the Pythagorean identity that relates secant and tangent, I have to get it from this one. All right, so I know if I want a secant in here, I need to put a cosine squared under here. And that helps me remember that that identity is tangent squared x plus 1 equals secant squared x. We're trying to write everything in terms of tangent. So I am going to replace this secant squared x with tangent squared x plus 1. And that is going to give me integral tangent squared x plus 1 times tangent squared x times secant squared x dx. And now we're ready to do our substitution. So if we let u equal tangent x, that's going to make du secant squared x dx. And my integral becomes integral u squared plus 1 times u squared du. All right, and that's a nice simple integral. Let's distribute this u squared. And let me see. Nope, I didn't leave. I didn't leave enough room on the next page, so I'm going to have to go up here. All right. So I have integral u to the 4th plus u squared du. And by the backwards power rule, that's u to the 5th over 5 plus u cubed over 3 plus c. And of course, it's not about u, it's about x. So the final answer is tangent to the 5th x over 5 plus tangent to the 3rd x over 3 plus c. All right, so that is one example of how to deal with an integral that has tangents and secants. All right, so here are the general rules. The example we just looked at is an example of this second bullet. If the secant power is even, break off a factor secant squared x and convert the other secants to tangents, then substitute u equals tangent x. The other sort of easy scenario is when the tangent power is odd, because then you can break off a secant x tangent x factor and convert the other tangents to secants. And then your substitution would be u equals secant x. Now, there are a few cases where neither one of these strategies will work. I guess the obvious one would be if the tangent power is even and the secant power is odd. But this printed version over here sort of captures some of the details of other cases where it doesn't work. Well, for example, if the tangent power is odd and you don't have a secant x factor, all right, in any of those sort of miscellaneous cases, it could end up being integration by parts, or it could be what we call reduction. And what reduction basically means is that you play with it and create an integral that's a little bit simpler. And eventually you get it down to something that you can evaluate. All right, so these are the examples I'm going to show you. Let's switch over to the tablet. All right, so the first example is integral secant cubed x tangent cubed x. So this falls under the category of the tangent power is odd. And what the guideline said to do about that is to break off a secant x tangent x factor, which is going to leave me with integral secant squared x tangent squared x. And then at the end here, I'll have a secant x tangent x dx. Okay. So what I'm going for is to be able to do a substitution where this ends up being my du, which means I'm going to have to let u equal secant x, which means we have to convert this into secant. And rather than derive the identity again, why don't I just go back to the last example? Oh, shoot, I erased that part, didn't I? Okay. Well, I'm pretty sure that I did that recently enough where I remember that tangent squared x is equal to secant squared x minus 1. Okay. So this one ends up actually being pretty similar to the last one we did. All right, so the substitution is let u equal secant x, which is going to make du secant x tangent x dx. So my new and improved integral is going to be integral u squared times u squared minus 1 du. Distribute that u squared. That gives me u to the 4th minus u squared. And again, by backwards power rule, that's going to be u to the 5th over 5 minus u to the 3rd over 3 plus c. But it's not about u. Final answer is secant to the 5th x over 5 minus secant to the 3rd x over 3 plus c.